Hello, welcome to this new video of Math-S401 dynamic optimization. Today we're going to deviate from what we have done previously because we're not going to look at infinite horizon dynamic optimization models, but we're going to look at finite dynamic optimization models. And we will see that even for finite models, the concept of Bellman equations can have a lot of value when trying to solve these problems. So today I'm going to look at a particular kind of problem, which is called minimum of shortest path problems. So let's go to the whiteboard. So here I have drawn, it looks a bit complicated, but it's actually quite a simple network. So what do we have in this network? Here we have nodes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so you can think of these as nodes in a network. For example, a network between cities, then all of these are cities. Okay, and cities are linked to each other by, let's say, roads, right? So for example, there's a road from 1 to 2, this green one here, and then there's a road here and here, right? So all the green lines are roads between the cities, and you can only go from 1 to 2, so these are directed roads or arcs. Okay, and every arc has a number associated with it. And you can think of this as the cost of transversing the road. Okay, so if you go from 1 to 2, then you have to pay a cost of 3. And then if you go from 2 to 6, you have to pay a cost of 2, and so on. So the problem here with this network is I would like to go from 1 to 10, right? So I want to transverse this network, and I would like to do it at using the shortest path or the minimum cost, right? So this could be also distance or cost or something other that measures how painful it is to take this road. Okay, so you would like to find the path through this network from node to node using the green roads from 1 to 10 in the least possible way. So one way to do this would be to say, okay, let's take one particular road. Let's, for example, take the upper one here. Okay, so from 1 to 2 I have 3, and then plus 4 is 7, plus 3 is 10, and then plus 4 is 14. Okay, and then maybe I can go from 1 to 3 to this one here. So here I have 1, then 4 is 5, plus 3 is 8, plus 4 is 12. So this one is shorter. I don't take the upper one, but I take the shortcut, and you can do this for every road possible and then take the shortest one. Okay, so this could be a solution to my problem. Basically, this is called a brute force approach. You take every possible road that you can imagine through this network, and you take the shortest one, and you have solved your problem. Of course, we would like to find a more efficient algorithm or an efficient mean to solve this problem. Okay, and you can use this or do this by the use of a Bellman equation. Okay, so here for Bellman equation, you have to define a function that's the value of a state. So here, first thing that you have to decide upon is what is a state. Okay, and the state, I will denote a node by state, right? So I have V of a state S, and here I will use as states, I will use the nodes in the network. And V of S is going to be the shortest path from S to the node 10. Okay, so this is the shortest from S to the final node X. So I'm only interested in the path from 1 to 10, right? But we will see that the fact that we define it as a function of a state for an arbitrary node is going to actually solve the problem here. So let's, for example, look at our problem, right? So we would like to compute V of 1. Okay, I have no idea what it is, but basically, if I'm at 1, I can do 3 things, right? I can go to 2, I can go to 3, and I can go to 4. Okay, so if I go to 3, what do I have? Well, I have a cost of 3, plus then the problem of going from 2 to 10. And the best way to go from, once I arrive at 2, the best thing to do is to take the shortest path from 2 to 10, right? So my cost, if I go from 1 to 2, this is going to be at least 3 plus V of 2, right? Once I'm at 2, the best thing I can do is take the shortest path if I want to minimize my cost. If I go to 3, well, then I have to pay a cost of 1 plus V1. V3, sorry. If I go to node 3, I have to pay a cost of 1 and then take the shortest path from 3 to 10. If I go to 2, I pay a cost of 2 plus the shortest path from node 4 to node 10, which is V10. V4. Sorry. So if I'm node 1, I can do 3 things. These are my 3 options. What's the best thing to do? Well, the best thing to do is take the minimum of these 3, right? Because this is going to minimize the cost of going from 1 to 10. So what do I have? I have that V1 is equal to the minimum of these 3 things. And of course, we can not really take the minimum because we don't know the values of these 3 V's. Okay, but you can use the same procedure to compute V2, right? V2 would be 4 plus V of 5 or 2 plus V of 6, basically the minimum of these 2. And the same you can do for V3. It will be 4 plus V of 5, or if it's less, 5 plus V of 7, and so on, right? So at every step you can define V of all these nodes as V of the nodes further on in the network, and you can define the V of these nodes and functional V of these nodes, and so on. Okay, so what is going to be the ID? This is the recursion of the Bellman equation. Well, basically we're first going to solve the shortest path from these nodes, then subsequently the shortest path from these nodes, then subsequently the shortest path from these nodes, and so on. Okay, so we're going to solve the problem recursively. And this will, by eliminating paths that are not efficient early on in the stage, this is going to give them some efficiency gains later on. Okay, so in principle, if you have nodes x, right, then you can, S of x, you can take this to be the set of successors. Okay, so these are all the nodes that are linked to a node x, right? So if this is x, then S of x will be this node and this node. Okay, so basically V of x will be equal to minimum over all y that are successors of x of the cost of going from x to y, right? You can denote this by C of xy, right? So for example, C12 is 3, C13 is 1, and so on, plus the minimum cost of going from y to 10. Okay, so in general, for this problem here, this is what we will have the Bellman equation. Okay, so this is the Bellman equation for our shortest path problem. And of course, because these recurses, right, this will be a function of S of y and then so on. We have to start with something, right? We have to start with the base case. You always, in these finite dynamic optimization models or dynamic programming problems, you always have to start from a base case. And here the base case is that once I'm here, I have to stop, right? So V of 10 is going to be equal to 0. Okay, so let's try to solve this here recursively using this tree. This is simple enough to do it on paper. Well, here my optimal cost will be equal to 0. Okay, because V of 10 by definition is equal to 0. Now, in order to compute the shortest path from here to here, I have to look at all successors of this node, but there's only one. So I have here 4 plus 0, which will give me a shortest path of 4. For this node, I have 3 plus 0, so this will give me shortest path of 3. If I want to solve it for this node, well, either I can take 3 plus 4, which will give me 7, or I can take 2 plus 3, which will give me 5, and 5 is shorter, right? So this will give me 3 plus 2 is 5. And maybe I can also color the the shortest paths, right? So this will be the shortest path from node 8. This will be the shortest path from here. Here the shortest path was the 2 here. Okay, by storing the solution, I can easily backtrack when I'm done, as you will see. From this node, either I take this road, from this node, right, I take this road, 2 plus 4 is going to give me 6, or 1 plus 3 is going to give me 4. Now 4 is clearly smaller, so I will take this path here. And for this node, either have 4 plus 4 is 8, or 6 plus 3 is 9, 8 is smaller, so I will take this path here. Okay, so every time I'm solving the problem recursively. From this node, either I take this path as 4 plus 5 is 9, or 2 plus written 4 is 6. 6 is shorter here, so I will take this one. Here, either have 4 plus 5 is 9, or 5 plus 8, which is 13. So here, this one is going to be shorter with a value of 9. From this node, either I have 3 plus 4 is 7, or 1 plus 8 is 9. So here the 7 is the shortest path. So it's this one. And you see, once I have solved these ones, I don't have to continue on, right? So this is a lot of efficiency gain. And now finally, from the starting point, either I have 3 plus 6 is 9, or 1 plus 9 is 10, which is bigger, or 2 plus 7, which is 9. So here I have a minimum path of 9, and here I have a tie, right? So I can either go this way, or I can go this way, which will give me the same cost. Okay, so and now I can clearly see the minimum path. I go from 1 to 2. This 1 to 2. So let me write it down. 1 to 2, and then 2 to 6, and then 6 to 9, and from 9 to 10. Okay, so this is one solution, or I can go from 1 to 4, 4 to 6, and then I continue as I did before to 9 and then to 10. Okay, so this gives you the solution using this idea of Bellman equation. Okay, so we will see in the remaining part of this lecture several of these types of model, and each time you will try to get a Bellman equation of this type, where you basically solve a problem by solving a simple minimizing or maximizing model and then recursing on some part of the model, right? And here the recursion is on the layers, you can say, or the layers of the path towards the endpoint. So this is the second kind of shortest path problem, and we're going to solve it again by using dynamic programming. So there's a bit different than the previous network. So again, we have a couple of nodes, 1, 2, 3, 4, 5, and we have connections between the nodes. For example, from 1 to 2, I can go with a cost of 6. From 2 to 5, I can go with a cost of 7, and so on. Okay, but there's a bit of a difference here. So first of all, it's possible that you have cycles in the path, right? So for example, from 2, I can go to 4. And from 4 I can go to 3, and from 3 I can go back to 2, right? So this was not the case in the previous network. Here I can have cycling, and I can also have negative costs, right? So maybe profits if you take this path, right? So here the question is a bit different, right? So you take any two nodes, let's say A and B. So the question is, what is the shortest path from A to B? Okay, so for example, what's the shortest path from 1 to 2? Well, it's possible to go directly from 1 to 2, then you get a payoff of 6. But for example, I can also go from 1 to 5, from 5 to 4, from 4 to 3, and from 3 to 2, right? Taking the big detour, as it may. Well, then I have minus 4 plus 3, so this is minus 1. Minus 5 is minus 6, plus 4 is minus 2. So if I take the big circle, I have a cost of minus 2, the direct one of 6, so this one is cheaper, right? So it's not immediately that the direct connections are the best ones. So the question is here, given any two nodes, what is going to be the shortest path? All right, so you may think of this problem, how are you going to solve it? So first of all, before we solving it, there's one remark that we have to make, and that's that we cannot have cycles in this network where the total cost is negative. Okay, so for example, if here this path, which is by the way not negative because it's 4 plus 1 and minus 5, which is 0, which is fine. But if this would be negative, then I can go from 2 to 2 with negative costs, right? I can keep on cycling, and so on. So basically I can find a path which cost is negative infinitely small, right? So this is not allowed because then the shortest path from a node to another node is basically not very well defined. In particular, I could say, for example, I go from 1 to 2 by going to 2 and then cycling around in 2, and I can make the cost as small as possible that I want. Okay, but anyway, given that I have a network like this and there's no cycle with negative total cost, I can in fact compute the shortest path from any node to any other node. But how do I do this? Right, that's the big question. I can try to take a brute force approach, try to find any path connecting two nodes, but here it's going to be even more difficult than in the previous network, right? Because I can have cycles, I can make big detours, maybe come back to a node, and so on, right? So it's not clear at all how to even enumerate all the possible paths between two nodes. As in the previous case, I could also think of, okay, let's start at B and try to work back recursively, right? But again, here this is going to be more problematic because there's not a clean order from the first node to the last node, right? What's here in this network the first node? I have no idea, because at this node some arrows enter, some arrows leave. I think at every node some arrows enter, so there's not really a starting point here. Okay, but if I want to make a Bellman equation, I want to write V of, let's say that V of AB is the shortest path from A to B. I would like to write this as some problem involving maybe the V function, but recurses on some smaller problem, right? So we can first solve the small problem, and then using the solutions of the small problem go to bigger and bigger problems. Okay. So if you want to sort it out for yourself, you can pause the video now and think about how you could try to solve the problem. If not, I will explain what these authors actually found to do. So the idea is not too difficult once you know it. Okay, so you have the node A and you have the node B, and you would like to find the shortest path from A to B. Okay, and this might involve intermediate nodes. Okay, so let's say that these are intermediate nodes, and then you go from A to some nodes in these intermediate nodes, then you follow some path between these intermediate nodes, and then finally you go to B. Okay, so let's assume that this is you have solved this problem for a subset of nodes S. Okay, so this is just you know the shortest path from A to B using nodes in S. Okay, that's what you know. And now you're going to recurse on this set S by trying to go to S union K for some node K, right? So you would like to add a node K to this subset of nodes here. So for example, this one. Now, how can you do this? Well, basically you can say, okay, maybe the shortest path from A to B using intermediate nodes in S union K. So there are two possibilities, right? So path from A to B using nodes in S union K, there are two options, but either they involve K, right? So K is on this path, right? Or it does not involve K. Okay. So if it does not involve K, then it's very easy, right? Then basically the optimal path, right? So now you're adding K here. The optimal path from A to B only goes via the nodes in S. Okay. So in this case, if I take the shortest path from A to B using nodes in S union K, right? Let me write it like this. Then this will be equal to V of S. V AB using only nodes in S. Okay. Now assume that it involves the node K. Then how is the path going to look like? Well, first of all, the path is going to maybe go through some nodes in S, and then it's going to hit the node K. Okay. And then from K starting, it is going to B and maybe also involve some nodes in S. Okay. So if it involves K, well then I know that the cost from going from A to B using nodes in S union K is going to be equal to the path from, first I'm going to go to K using nodes in S, plus I'm going to go from K to B also using nodes in S. Okay, and here we can see that we have solve the problem when S, the intermediate set is S union K, by recursing on smaller problems only using nodes, intermediate nodes in S. Okay, so let me write down the problem again. Let S be a subset of nodes 1, 2, and so on until K. Well then, the value or the cost from going from some node A to B using the nodes in S, so this already includes K, right? It's going to be equal to either, if this path goes through K, well then it's the value going from A to K using the nodes in S minus K, plus the value of going from K to B, again using nodes in S minus K, or it's going to be equal to the value of going from A to B using only nodes in S union K. And of course I'm going to take the minimum of these two. Okay, so that's basically how it works. And you have seen that now we write this value function that depends on S as value functions that depend on S minus K. So we can do this recursively. So for example, you can start with S equal to the empty set, then we have S equal to the set only containing node 1, then you have S containing the node 1 and 2, and so on until we have S containing the nodes 1, 2, until the last one. Let me call this begin. I don't know which one is the last node, right? So first we solve for VAB empty set, and we do this for all A and B, right? Once we have this, we solve for AB, all the paths. What's the shortest path from going from A to B using only the intermediate node 1? Then you compute the shortest path from going from A to B using the intermediate nodes 1 and 2, and so on. Okay, so this is how we recurse on this for some order of the nodes. Okay, let's try to see how this works in practice. So here what I have written down is a table, right? It's basically the table of distances. So here I have the nodes, here I have also the nodes, and each entry gives a distance between two nodes, right? So for example, the distance from 1 to 1 is equal to 0, the distance from 1 to 2 is 6, right? Because there's a path from 1 to 2, that has a cost of 6, right? So this is the costs of the direct costs of going from some node to another node. And I have put infinity if there's no direct link, right? So there's no direct link between 1 and 4. So here I put the cost infinity. So here, this matrix here lists, should use blue, C of going from some node A to the other node B of using the empty set as intermediate nodes, right? So this is basically this table gives all the values of this function here. Okay, so it should be V, sorry. The cost of going from A to B using 0 as the intermediate nodes. Now let's assume that I would like to compute VAB using the intermediate node 1. Okay, so this is the first step in my algorithm. So going from 1 to 1 using intermediate nodes 1, so there's not going to be a change here, right? Because you're starting at 1. So it's not going to help you using the intermediate node 1, right? So here these values are all going to be the same. Okay. Also in this column here, because you're arriving at node 1, is not going to help you by using the intermediate nodes 1. So here also, this is already easy. You can already fill this in. Now let's look at also the diagonals, sorry, staying at the same node. So it's going to be 0, so all these values are going to stay fixed. Now let's, for example, look at this entry here, right? So here you're going from node 2 to node 3, which has a cost of infinity, but I'm also here, I'm allowed to go first to node 1, and then from node 1 to node 3, but from 2 to 1 is already infinity, so this is not going to help you, so this is going to stay at infinity. From node 1 to node 4, again, if I go via 1 first, I first have infinity, so here this is not going to help me, so this is going to stay the shortest path. And also here from 2 to 5, using 1 as an intermediate node is not going to help you, because from 2 to 1 is going to be infinity. Right, so you see that if the intermediate node has a cost of infinity, this is already not going to help you. So also in this row here, all the elements are going to be the same. Okay, so here node 1 is not going to help you. So here we have a potential benefit, right? So the cost of going from 4 to 2 was infinity, but if I first go from 4 to 1, I have 2. And then from 1 to 2, I have 6. So this will give me joint cost of 8. So here I have an improvement. Okay, so this will turn out 8. Well, could this be improved? So if I go from 4 to 2 via 1, I have 2. And from 1 to 3, I have 8 is 10. But this is minus 5, so this remains the same. All right, so this doesn't help me. Maybe this one could be improved. All right. If I go from 4 to 1, I have 2. From 1 to 5, I have minus 4, so this is minus 2, which is better than infinity. So here I have a gain. Okay. Here, this is infinity, so adding 1 is not going to help me. So this is going to stay the same. But we have some updates in the table, right? So for some combination of nodes, we have found a shorter path. So let me replicate this table and then continue. Okay, so here I have replicated the red table above, right? So here we have the cost from going from some node to another node using potentially the node 1 as an intermediate node. So now we're going to add one more node to this set of intermediate nodes. So we're going to compute the cost of going from node A to node B using, for example, two intermediate nodes 1 and 2. Okay. So first of all, adding 2 to compute costs involving node 2 is not going to change. So we can already put all of these in red. Also the diagonals are going to be in red. These are going to stay at 0, no problem. And also arriving at node 2 is not going to help any value here in this table. Okay. So the first one here is going from node 1 to node 3. I can also, now I have to look at the possibility of first passing through node 2. Okay, so if I first go from node 1 to node 2, I have 6, and then from node 2 to node 3 as I have infinity, so 6 plus infinity is infinity, so 8 is here still the optimal solution. From node 1 to node 4 I have infinity, but I can go first through node 2 here. So 1 to 2 is 6, 2 to 4 is 1, so this is going to improve the value to 7. 1 to 5 was minus 4. If I go via 2, I have 1 to 2 is 6, 2 to 5 is 7, 6 plus 7 is 13, so this minus 4 is smaller than 13, so this stays at minus 4. Let's look here. 3 to 1 is infinity. If I first go via node 2, I have 4, and then 2 to 1 is infinity, so this is not going to help me because 4 plus infinity is still infinity. 3 to 4 is infinity. If I pass through 2 first, I have 4, and then 2 to 4 is 1, is 5. So this will update to the value of 5. Here it's infinity. 1 to 2 is 4. 2 to 5 is 7. 4 plus 7 is 13. So this updates to 13. Here the direct connection is 2. If I pass through 2, I have 8 plus infinity, so this remains here at 2. Minus 5, if I go via 2, I have 8 plus infinity. It's not going to help me, so this is staying at minus 5. Here I have minus 2, right? So if I pass through 2 first, I have 8 plus 7, which is 15, so this also doesn't help me a lot. Here I have infinity. I can first go to node 2. I have also infinity. Infinity plus something is going to stay at infinity, so this is going to stay the same. Here, every time I pass first via node 2, I have infinity, right? So these are also not going to change, right? So I have a couple of values that are updated and other ones that remain the same. Again, let me copy the table and then come back to you. Okay, so I have copied this table. Now let me compute by adding another node the minimum cost of going from A to B using intermediate nodes 1, 2, and 3. Okay, so the diagonals won't change. Also, every node leaving 3 will not change. Every node arriving at 3 will also not change. Alright, so these are the red ones that we can already fill in. 1 to 2 is 6. If I go via 3, I have 8 plus 4 is 12. 6 is smaller than 12, so this remains at 6. 1 to 4 is 7. If I go using 3, I have 8 plus 8 plus 5. This is 13, so 7 is smaller, so this remains the same. 1 to 5 is minus 4. If I go to 3, I have 8, and 3 to 5 is 13. 8 plus 13 is 21, so minus 4 is smaller. So nothing changed in the first row. 2 to 1 is infinity. First I can go to 3. This is infinity, and then 3 to 1 is infinity, so this remains at infinity. Nothing here. Here I have 1. If I go to 3, I already have infinity here, right? So 1 is going to be smaller anyway. Here I have 7. Again, using 3 first is infinity. So this is not helping me, right? So because from 2 to 3 is already infinity, going via infinity is not going to help me at this row. Here, maybe I get some benefits here for the row for 4. Here I have 2. If I go to 3 first, I have minus 5. And then from 3 to 1, I have infinity. So this is not going to help me. This remains at 2. Here I have 8. Going to 3 first is minus 5. And then from 3 to 2, I have 4, which is -1. So here I have a -1, which is better than the 8. Okay, so here I have a gain. Here I have -2. If I go to 3, I have -5, and then plus 13, which is 8. So -2 is better here. Here for 5, if I go first from 5 to 3, I have infinity, right? So whatever happens here, I have no efficiency gain. So this remains at infinity and this remains at 3. Okay, so this is the updated table for this cost. I have 2 more to go, so let me copy this one and then come back. Okay, so we do the same exercise, but now we look at nodes that also pass through 4. So again, the diagonals stay at 0. Everything leaving 4 or arriving at 4 is not changing. From 1 to 2 I have 6. If I go to 4 first, I have 7, and then 7 to 2, 4 to 2 is -1 is 6. So 6 or 6 remains at 6. Okay, 1 to 3 is 8. 1 to 3 I have 8. First I go to 4, and then from 4 to 3 is -5. So 7 minus 5 is 2. So this gives me a gain to 2. Okay, 1 to 5 is -4. If I go 7 first, and then from 4 to -2, which I have 7 minus 2 is 5. -4 is smaller, so there's no gain here. Okay, so this is a bit tricky, right? You have to stay focused when doing this kind of exercise. So from 2 to 1 I have infinity. First I can go to 4, which I have 1, and then from 4 to 1 I have 2, so this is 3. So this helps me here. Here also I have infinity. If I go to 4 first, I have 1, and then from 4 to 2 I have -1, if I read correctly. So this is 0, but I already, okay. So so here I have infinity, right? So this is 1, and -5 is -4. So this is an infinite improvement, right? So I have a -4 here. Here I have a 7. If first I go to 4, I have 1, and then from 4 I have to 5 I have -2. 1 minus 2 is -1. Okay, so adding 4 to the program improves my costs a lot, apparently, for this problem. Okay, so this row, 3, I have infinity. 3 to 1 I have infinity. 3 to 4 I have 5. 4 to 1 I have 2. 5 plus 2 is 7. Also improvement here. 3 to 2 I had 4. If I go via 4 I have 5. -1 is 4. So here this stays at 4. Here I have 13. If I go through 4 I have 5. 5 minus 2 is 3. So this changes to 3. And now for the last row, here I have infinity. If first I go to 4 I have 3. Here I have 2. So this becomes a 5. This one here becomes a 3 minus 1 is 2. This becomes a 3 minus 5, which is going to be -2. And this stays at 3 and 0. Okay, so this is now my updated table for this problem, and I have one more to go. Okay, so I already did it in a very quick way. I already filled in the table for the last one in order not to make the video too long. All right, so this is 1, 2, 3, 4, 5. So this is going to be my final cost table because I allow for any other node to be intermediate nodes of the shortest path. Right, so finally we get a table with this cost. So I know that the shortest path, for example, from 1 to 2 is going to be -2. Okay, so this was a long detour. If I have it correctly, this was this part here. Okay. So it's interesting also to look at how complex this problem is to solve on the computer, right? How many steps do we need to make in order to solve this problem? So let's, for example, take a network with n nodes. And what do we need to do, right? So for every set of intermediate nodes, right? So how many were there? We started with an intermediate node equal to the empty set, right? This was basically already given by definition. Then we added one node, then we added one node, and then we added one node, right? So basically we add n times one node, right? So basically we had n tables to fill in, right? The first table, the second table, the third table, and so on. And how many entries do we need to update every time? Okay, so basically, yeah, we had n times n, so n squared entries in the table. So this is of the order n squared entries, right? So basically we had n squared values a, b that we needed to update. Okay, so we n squared times you compute n tables, so in total we have something like in the order n to the third running time. We call this operations to do, right? So this is called the complexity of the problem, which is of the order n to the third, right? So in principle, in computers or in computational complexity, you have things that are polynomial in the input. So here n is the input, and you have things that are exponential in the input. So maybe of the order en. Things that are exponential are normally considered to be very inefficient, right? Takes a long time to compute. Things that are polynomial are normally considered to be efficient, very quick to compute. Yes, so here we did it manually, and with a network with 5 nodes, you can still do this manually. You can imagine that if you have to do this, for example, for 100 nodes, that it will become very tedious at some point to fill in all these values, right? So normally we solve these kind of problems by using a computer. So let me show you how to do this, how to write such kind of code in a computer program. Okay, so here we're in Julia. So what I've done so far is I already wrote down our initial distance matrix, right? So this is the first table that we have seen. So distance from node 1 to node 1 is 0, from node 1 to node 2 is 6, and so on, and we have infinities if there's no direct connection. Okay, so let's write a function, shortest path, and it's going to take in a distance matrix D. So here we're going to, basically what we're going to do is we're going to run this function, and we're going to give it the input dist, right, the distance matrix. Okay. So first thing that we may want to do is compute the number of nodes. So this is simply the length of the, let's say the first column of D is going to give me n. And what we maybe also want to do is we want to store not only the distances from a particular node to another node, but we also want to store the path that actually gives you the shortest distance, right? And the path we can store it by using a vector of a sequence of nodes. And this is basically what we're going to do. So we're going to use for this, so we're going to store it in path, and this is going to be a dictionary. So a dictionary is basically something that you can use to store key values, and the key can be anything that you want, and then the value can also be anything that you want, and the value is associated with the key. So here for the key we're going to use 2 nodes, the starting one and the end node. So we're going to store it in a tuple. It's going to take one node and then another node, which we're going to store as integers, and then the value of the key, this is going to be a path, and we're going to store this as a vector, right, of nodes of integers here. Okay, so here we're going to initialize this path, and at the end we're going to return the new distance matrix, right, so the last table and also the shortest path from the end start to the finish. And we're going to initialize the path. So initially for this table here there will be, for example, a path from node 1 to node 2, that's 1, 2, but no path from node 1 to node 4 because there's infinity here, right? So for the first node from 1 to n, and then for the second node 1 to n, we're going to, if d, right, so the distance matrix here, distance between I and j is less than infinity, we know that there's a direct connection between the two. Yes, O2 complete. If there's a direct connection to the two, we're going to set path from I to j. This is going to be simply the vector ij, right? We can know that there's a direct connection between the two. And then else, we're going to set the path from I to j. We're going to initialize this to be the empty path, right? There's no direct connection between the two. Okay, so ending all the loops. So if I run this now for the distance, shortest path is not defined because I forget the capital P. This one is defined. So what's now I'm simply going to return the same matrix, right? So there's nothing computed yet. And now, for example, there's no direct path from 4 to 5 because I have a vector of dimension 0. There's a direct connection from 1 to 2, and it's the path 1 to, right? So this is basically how I'm going to store these paths. Okay, so I have to compute these tables iteratively. So remember what I had was the cost of going from I to j using a set of intermediate nodes, let's say 1 to k. Well, this was either was the minimum of c ij of 1 k. Okay, then the second argument was maybe it's the distance from ci k taken 1 k minus 1. Okay, so this is k minus 1, the recursion. Let me write it different, right? Taking intermediate nodes up to k was Cij taking intermediate nodes up to k minus 1, right? Or taking the distance from I to k using intermediate nodes to k minus 1 plus Ckj using intermediate nodes up to k minus 1. Okay, so this was basically my Bellman equation, and I would like to program this. Now these ones will be stored in this D here when I iterate the tables, right? So it will be stored in the table. So if the distance from I to j is less than the distance from I to k plus the distance from k to j, well, if this happens, I'm going to update dij to be equal to dik plus dkj, and I'm also going to update my path ij. So now I have found a shorter path, first taking the path from I to k, and then using the path from k to j. Alright, so so this is taking the first path and then the second path, but now we cannot use addition, right? Basically we're concatenating two vectors, right? And we can use the vcat operation to do this. So we get the vector here and the vector here, and vcat basically stacks one vector above the other one. When we do this, there's one tricky thing here. So this is a path from I to k, and this is a path from k to j. So if we add the two together, we will have two k's, right? One at the end here and one at the start here. And so this is not very nice. So basically what we want to do is we want to delete one k from this path in the middle. So we're only going to take the second path from the second node until the end, right? So basically this is what this 2 to end does. So this is a vector here. Take this vector, but we only consider it from the second element until the end. Okay, so this is going to update my table. And of course you have to do this for every I and every k, right? So for I equal to 1 to n, and for j equal to 1 to n. We're going to update this here and update this here and end, right? So this is going to compute every entry in my table. And then of course you have to do this k times, right, iterating over the different tables. So we're going to have a loop for k equal to 1 to n of all this. Basically we're going to have 3 nested loops, right, over k, over I, and over j. And this basically should finish my algorithm. Okay, so let's load it here. I have written my table distance, and now, so I compute new distance will give me the new table, and then the path will give me the shortest path. Okay, so if I look at the new distance entry, oh, this is not very nice, it's infinity everywhere. So why did I do this? Oh, this should not be smaller but bigger, right? So if the distance between ij is bigger than the indirect distance, I have to update my table. Okay, so this is why I got infinities. Let's see if this improves now. No, it's still infinity. Maybe I have to read it in here. Yes, this looks better, right? So now I have, if I look at my vector new distance, I have 0, -2 as a path from 1 to 2, right? This was this indirect route. And if I now look at paths from 1 to 2, how does this path look like? Well, it's a vector with 5 elements. I start at node 1, then I go to node 5, then I go to node 4, to node 3, and then to node 2. Right, so you can do this for every possible path, right? For every possible path. For example, from 5 to 1, I go from 5 to 4 to 1. Okay, and then I can also compute 5, 1 as a distance of 5. Okay, so this is how you code up this problem. Thank you for watching.